back today to finish up our discussion of correlation coefficients. In the first video, we discussed the logic behind correlation coefficients, and we indicated that there's a statistical test of significance of that correlation coefficient, and that's what we're going to cover today. Before we get to that, I want to show you some additional ways that correlation and scatter plots can be used to assess how correlations work. Here's some idealized shapes of correlation coefficients shown by their scatter plots. In the upper left and lower left graphics, you can see that there's a reasonably high correlation coefficient. The correlation coefficient for both graphics is 0.6. It's positive 0.6 in the upper graphic and negative 0.6 in the lower graphic. And this is partially to show you that regardless of the direction of the relationship, these two correlation coefficients are equal to each other, and therefore the degree of association, or the strength of the association between these two variables, are identical. One just happens to be negative, the other positive. It would be incorrect to say that the negative 0.6 correlation is less than the correlation of 0.6. Some people like to look at the absolute value because we really don't care if it's negative or positive, except when we interpret the direction of the coefficient. When we look at magnitude, we look at the absolute value. The graphics on the right, the upper right and lower right, indicate a perfect correlation between two variables. Again, one positive, the upper graphic, and one negative, the lower graphic. You won't see these in reality. These are really more of a mathematical function than a statistical function. We have several sources of error. We have measurement error, we have sampling error, and then of course people make decisions that aren't always consistent. And so we have free will. Those things lead us to find relationships that are not perfect like this. When I say that a relationship's perfect, it means that if I know the value of the independent variable, I can make a prediction about the dependent variable with no error. So think about the predictions we talked about in the analysis of variance videos and lectures, and it's the same kind of error we're talking about there. If my group membership is important, in fact so important that nothing else matters, knowing what group an object belongs to will allow me to make a perfect prediction about some value on a dependent variable. If you see a correlation coefficient of 1 or minus 1, it probably means you've made some kind of mistake. You're either correlating a variable with itself or with a measure that is so close to it that they're basically identical. There are a couple patterns that illustrate how correlation coefficients can also be misleading. Take a look at this graphic. You'll notice that there's two lines drawn through this graphic. And you'll also notice in the upper right corner there's a set of outliers. We said before that one of the problems with correlation coefficients is that outliers can influence the correlation coefficient. For this particular graphic, I've calculated two correlation coefficients. One that includes all those points that are circled in the upper right, and that correlation coefficient is 0.22. The other correlation coefficient excludes those cases and looks only at that big cluster in the middle. That correlation coefficient is, for all practical purposes, 0. So which is the correct correlation coefficient? 0.22 or 0? If I see a graphic like this, I have a concern that I have somehow miscoded my data, entered some data incorrectly, or have made some kind of instrumentation error that leads those outliers to exist, and they really don't belong there. So that means I have to go back in my early steps of data collection and data processing to make certain I've done everything properly. If I've done everything properly and those cases are real, the values are actually accurate, then I want to look at those cases and see if there's something different about them. Are those all men or all women? Are they all people of a particular religion? Is there something that makes them group together and behave differently? And if so, I'm going to try to model that in my correlation coefficient. That's a little bit more advanced topic, one that we're not going to cover here, but I would have concerns about it. If I don't have any reason to believe that the data are somehow incorrect or inaccurate, or that there's a third variable operating here like religion or gender or race, then I'm probably going to leave them in my model and conclude that the correlation coefficient here is 0.22. But understand that when statisticians and analysts and researchers look at data like this, they might make a different decision than that. And this is a bit of a subjective call, but it's one that you may have to defend at some point if somebody sees the same graphic and feels differently than you. In this particular example, those outliers, being far away from the mean of x and the mean of y, are influential in our Pearson's correlation coefficient, and in this case, make it larger than if those cases were excluded. So this is an example of how outliers can influence our Pearson's correlation coefficient. Moving to the graphic on the lower left, I've calculated again two correlation coefficients. One correlation coefficient is for the cases that are just enclosed in that box in the lower left of the graphic, and that correlation coefficient is 0.11, a relatively low correlation coefficient. If I calculate the correlation coefficient for all of the cases, both inside that box and outside, my correlation coefficient goes to 0.11. The point here is that when we make a generalization based on a correlation coefficient, we want to be pretty specific about what it is we've measured. For example, if I was discussing the relationship between age and income, where age would be our independent variable and income our dependent variable, and if I had access only to the data in that box, that would be consistent with having a sample of young people, I would conclude that there's virtually no relationship between age and income. And that's probably an okay conclusion as long as I acknowledge that my sample is really not a sample of all people, it's just a sample of young people. Because we can see that when I relax that age restriction and look at all ages, in fact there's a reasonably strong correlation and association between income and age. Whereas people get older, we see an average increase in their income. So again, this is another example of how correlation coefficients can be misleading unless we properly specify our model and where our data come from and how they're measured. The final example also plays off the same kind of problem that we saw in the first graphic. That is, outliers can increase or decrease our correlation coefficient. So here, again, I've drawn two different samples, one with the outliers in the lower right, and I've correlated the independent and dependent variable, and I get a correlation coefficient of 0.78. If I exclude those cases circled in the lower right, my correlation coefficient increases to 0.9. So which is the correct correlation coefficient? Again, I need to determine if the data are correct and accurately represent the underlying things I'm trying to measure. I need to find out if those outlying cases are somehow collectively different or homogeneous. And if not, I may end up going with my 0.78 correlation. Otherwise, if I have an instrumentation error, I may choose to exclude them and make a footnote in my paper or my research project so that people understand that I found these undesirable cases or I couldn't seem to code them properly and I excluded them. Well, once we have a measure of correlation, we'd like to have some measure of statistical significance. And to do that, we're going to have to develop a sampling distribution. You may remember from a long time ago we talked about frequency distributions for one variable, univariate frequency distributions. But here we're looking at variables in two dimensions, two different variables. So I've got my scatter plot of my verbal score and my math score. Now I could take those scores and I could draw a grid over that, and I could count the number of cases in each grid, and then I could pull that bar or extrude it up off that flat surface so I could get a three-dimensional frequency distribution. And that's shown in the graphic on the right. If I were able to increase my number of cases, and I could decrease the width of my intervals, and I could do this over and over and over again, I'd eventually be able to create a graphic that looks like the one at the bottom, which would be a smoothed graphic. It's a cumulative probability distribution where the probability of a correlation lies on the surface of that object. What's interesting about this particular distribution is if I were to cut a slice of this distribution and pull it away, kind of thinking of it like as a big piece of cake, and I go along that line y sub 0 or x sub 0, and I cut a piece and I pull it away, if I were to sight at this graphic, kind of get down low to the table and look at it head on, I would see a univariate distribution, and it would be normally distributed. Taken together, these two variables are jointly or bivariately normally distributed. This is a picture of a sampling distribution that has every possible correlation coefficient I could get based on repeated random sampling. So, like other things we've discussed in the course, this is a picture of how chance operates on a particular statistic, in this case correlation coefficients. You may have already guessed by now that the actual calculation of the test of significance is different than what we've done before. So to review, we have a hypothesis testing framework with approximately 5 steps. All the steps share a lot in common, Step number 4 is the one that has the most differences because that's the one where we actually calculate the statistic. We've calculated a t statistic, an f statistic, a chi-square statistic, and now we're going to calculate a t statistic as well. And we're going to put a confidence interval around our correlation coefficient and use that to do a test of significance. There's a couple of ways to do these significance tests, and I've elected to teach you one method, and that's to put a confidence interval around our correlation coefficient. So what we're going to do is we're going to calculate Pearson's R. We'll put a confidence interval around it, and if 0 falls within that confidence interval, we'll fail to reject the null, knowing we may have made a type 2 error. If 0 doesn't fall inside that confidence interval, we're going to reject the null, knowing that if we've made an error, it's a type 1 error, and that the probability of making a type 1 error is equal to whatever our alpha value used in creating that confidence interval. This is a pretty good method, and it also demonstrates to us what our null hypothesis is. The null hypothesis in this case is that our sample correlation coefficient is equal to 0. If it's equal to 0, then it should fall within our confidence interval, and if it's not, it should fall outside. I like this particular test because we can use it with small samples, we can use it with non-normal populations, and if we wanted to, we could test values other than 0. That is, we could hypothesize that the correlation should be, for example, 0.3, and then in our numerator we would simply have the difference between our observed correlation coefficient and 0.3 and divide by a standard error. As I said before, the steps involved in calculating this statistic are different than the other statistics we've calculated. But here's the basic outline. There's 3 steps. The first thing we're going to do is take our Pearson's R and we're going to convert it to a new statistic called Z. This has nothing to do with the Z distribution, but it's again an unfortunate thing that some statistician named Z, and some people get it confused with a Z distribution or a Z score. This particular distribution, instead of ranging from -1 to 1 like our Pearson's correlation coefficient, is unbounded, and it has a theoretical range of -infinity to +infinity. We're going to take that new number Z and we're going to put a confidence interval around that the way we normally put a confidence interval around things. That's step number 2. So we're going to take Pearson's R plus or minus some t statistic times a standard error. And then in step 3, we're going to figure out what the upper and lower bounds of our confidence interval are in Z, and then we're going to convert them back to R, so they're again on that scale of -1 to 1. We then check and see whether 0 falls in that interval, fail to reject the null, or whether 0 falls outside the interval, and we reject the null. So step 1 is very easy. There's 2 different formulas you can use. The formula that I like is the one on top. The only difference between them is one uses log base 2.718 and the other uses log base 10. You'll get the same answer regardless of which formula you use. So to use this formula, you need to figure out the log key on your calculator or your spreadsheet, and you need to have the correlation coefficient. If you have that, it's a very simple matter to go ahead and calculate or to convert a particular Pearson's R to a z-score. Then we need the standard error. Well, in our particular problem for correlation coefficients, it's pretty easy. Our standard error is simply equal to 1 divided by the square root of n minus 3. So notice that this is given as sigma sub z sub r. That is, it's the standard deviation or standard error of a z distribution of an r variable. So in our example of this math and verbal score, there were 8 individuals, and so my standard error is 1 divided by the square root of 8 minus 3, or approximately 0.45. Down at the bottom, you can see that I have the confidence interval, and it's the same kind of confidence interval we saw before. So for a 95% confidence interval, we'll take our z sub r score, and we'll make that plus or minus some margin of error, which is equal to t divided by our standard error. And where does the t statistic come from? The t table in the back of the book, just like we use for our other confidence intervals. Now that we've converted our Pearson's R to Z and we've calculated our standard error, we can simply calculate our 95% confidence interval around that value of Fisher's Z. You can see the formula is pretty easy. It's going to be our correlation coefficient as a Z-score, 0.741, plus or minus the margin of error, which is equal to our Z statistic. With alpha 0.05, we'll use 1.96 times our standard error, and that's 0.741 plus or minus approximately 0.88. So our confidence interval in Z then extends from minus 0.136 to 1.618. So there's our confidence interval, and looking at that I can tell right away that I'm not going to reject the null hypothesis, because 0 has to fall in that range, minus 0.136 to 1.618. Fisher's Z is not the most meaningful metric, so now we have the task of converting this back into Pearson's correlation coefficients. I'm just going to show you what the values are here, and then I'll show you a table that you can find in the back of a lot of different statistics texts or online that will get you pretty close to the right answer. So in Z, we know that our lower limit for our 95% confidence interval is minus 0.316, and our upper limit is 1.618. Using this table, I convert this back to Pearson's R, and I have my 95% confidence interval extending from minus 0.135 to 0.925. We can see that that range captures 0, 0 falls in the middle, so we fail to reject the null hypothesis. If 0 had fallen outside of that range, then we would reject the null hypothesis. Here's a Fisher's Z to R table from the back of a popular statistics text. You'll notice the columns are labeled R for Pearson's R and Z for Fisher's Z, so we can convert from R to Z or Z to R depending upon which column we start in. We've already defined or calculated our Fisher's Z as minus 0.136 and 1.618, so we need to look up those values in the table under the columns labeled Z. In the first Z column, I find the closest value to minus 0.136, which is exactly 0.136. Notice that there's no negative signs. I have to keep track of that. And I find the associated Pearson's R of 0.135. Now I look through the table for a Fisher's Z of 1.618, and the closest value I can find to that is 1.623 in the Z column on the far right. The associated Pearson's R is 0.925. So our Fisher's Z, when converted back to Pearson's R, has a 95% confidence interval ranging from minus 0.135 to 0.925. Let's look at one last example. We saw in that first table of correlation coefficients the relationship between age and sexual frequency. And we saw that the correlation coefficient for that particular relationship is minus 0.63, indicating that as people get older, on average, they report having sex less frequently. We can go ahead and solve this problem and create a 95% confidence interval and use that to test for significance. So let's go ahead and talk about our null and alternative hypothesis. The null hypothesis is that the correlation coefficient is equal to 0. The alternative hypothesis, and I'm using a two-tailed hypothesis here, is that the correlation coefficient is not equal to 0. The step 2, what's the appropriate sampling distribution? Well, when I do this kind of test, it turns out that the t-distribution is the appropriate distribution. Step 3, how much evidence do I need to reject the null? Since I'm using a confidence interval, I have to be doing a two-tailed test. And I'm going to do a 95% confidence interval, and that means that I'm using alpha 0.05. Step 4, calculate the statistic. Well, a little bit of two steps here. Step number 1, go ahead and convert the Pearson's correlation coefficient of minus 0.36 to some Z unit. When I go through that process and I use my log base E, I get minus 0.3769. Then I go ahead and calculate my standard error, which is simply 1 divided by the square root of n minus 3, and I get 0.0239. Notice how small that standard error is, and that's because I have a very large sample size here. And now the last thing I'm going to do is I'm going to put that all together, and I'm going to say that my 95% confidence interval is centered around my Z score of 0.3769, and my interval extends from the bottom of the minus the margin error plus plus the margin of error, or 1.96 times 0.0239. So down at the bottom, you can see that my 95% confidence interval in Z goes from minus 0.424 to minus 0.330. And when I use the table in the back of the book to convert those Z scores to R, I can see that my 95% confidence interval, while it's centered around minus 0.36, it extends from minus 0.4 to minus 0.32, a very small confidence interval. In this case, I'm going to reject the null hypothesis and conclude that this is a statistically significant difference. So I'm now in a position to interpret my correlation coefficient and assess the relationship between age and sexual frequency. First of all, we can conclude that the relationship is statistically significant with alpha 0.05. That's what our confidence interval tells us. Then we can talk about the direction of the relationship. We can see that as people get older, as they age, they report having sex less frequently than when people are younger. That's the direction of the relationship. And finally, we should talk about the magnitude of the relationship. That's a little difficult because we aren't converting this to number of times per year, which would help us assess this. But we do have the correlation coefficient itself, and we know that if it gets close to 1 or minus 1, it's a strong correlation. And I think we could conclude that this is a moderately strong correlation. Some books, I think the authors of our textbook, would call this a weak relationship. One last thing that we can do is we can also go ahead and calculate our R statistic as a T statistic. And I've given you the formula down below. That is, if we let our null hypothesis be that R is equal to 0, but we observe an R of minus 0.36, we can convert that to a T-score by taking our R and dividing by a standard error. Now I'm using a different formula for the standard error here, but you can see that I'm going to get the same result. I'm going to get a very large T statistic, and it's negative, so it has to be consistent with the direction of the coefficient. And I'm going to come to the same conclusion that I should reject the null hypothesis and conclude that these two variables are statistically correlated or related to each other. As usual, if you have any questions, please send them to us by email or catch us in class or drop by for office hours, and we'll answer all of your questions.